All right, so today we're going to take a look at an introduction to 2D kinematics, or another way you could say it would be 2D motion. So, just a little recap of where we've been. It says so far we've learned about objects that, number one, move only in the x direction. So, several weeks ago now, we talked about things like cars, runners, trains, where we're dealing with things that were accelerating. They had some initial velocity, they had a final velocity. We're looking for how far they went side to side. We said that was delta x, or horizontal displacement. And then after that, we said, okay, let's take a week and talk about things that move only in the y direction. And we call that free fall. So examples would be skydivers, or anything that's dropped, basically. So we did X, we did Y, and then the last probably week and a half here, we've been focused on doing what I call vector or vector math. So vectors talk about things that are moving through two dimensions, and we've been doing lots of things with sine, cosine, tangent, Pythagorean theorem. So now we're going to put all those three units together in something called 2D kinematics, sometimes referred to as projectiles. So it says number 3. Now we will study objects that are moving in both the x and y direction under the influence of gravity. These objects are called projectiles. So kind of a classic picture you can have in your head is if you picture a projectile. And I'm just going to go ahead and let's grab a pen down here and say we have something that's being launched. So some object like a ball. That's a horrible ball. I'll do better in the future. But we're going to launch a ball up at an angle with some initial velocity here, VO. And then now, since we're going to launch it at an angle, it's not moving just through the x or just through the y. It's moving through both the x and the y. So that would be considered a 2D kinematic problem, a projectile problem, because now we're going to get an initial velocity in the x and also an initial velocity in the y. All right, so before we get going too far, here's some key ideas about projectiles just to see kind of what we know already. So go ahead and read through the questions and then try your best to answer them, and then we'll come back and give you the answers. Number 1 says, if you wanted to launch something, for example, at its maximum vertical height, what would be the ideal angle to do that? And if you said 90 degrees, you would have been correct. If you want to throw something its maximum distance in the y direction, you can picture exactly horizontally would be 0 degrees, and 90 degrees would be straight up. So if you wanted to launch something vertically as high as it could go, you'd want to be at 90 degrees. Number 2, for maximum horizontal range, so basically you want your delta x to be the greatest, what would be the ideal angle? And technically we should say if there's no air resistance here. So if you're in a sport where you're having to throw things far, like a shot putter, or maybe you're throwing something or kicking something, the ideal angle for maximum horizontal distance would be 45 degrees. And then number 3, the acceleration from gravity acts only in the y direction. So gravity only ever acts in the y direction. This means that the vertical velocity is always changing as the object moves. So we kind of talked about that when we drop something, right? So you drop something, gravity only acts in the y, so it accelerates that object downward, which means that its vertical velocity will always be changing. Number 4 is important. The acceleration from gravity never acts horizontally. So when you throw something and it's going through the air, gravity doesn't affect its side-to-side velocity at all. And somebody might say, but I notice it slows down a little bit. Well, if it ever slows down side to side, it's due to the air resistance. But gravity does not act side to side. That would be kind of a strange planet if it did, because you'd throw something and it would actually gain speed as it traveled horizontally, and that's just not what we see. It says this means that the velocities in the horizontal direction always stay the same, or you could say horizontally the velocities are constant. All right, another warm-up. So we're doing 2 warm-ups so we don't pull a brain muscle here because there's lots of new terms. It says before we start using the motion equations, and I should say motion equations again, let's review. For each description, identify which variable is being described. So take a second, we'll do number 1 together, but take a second, just go through. These are things you might see in a problem statement. So number 1, horizontal displacement is 15 meters. So kind of think back, horizontal displacement, which variable would that be? And as soon as you see horizontal, you should start thinking about it's going to be the x variable, and displacement, we said, would be triangle or delta x. So for number 1 there, horizontal displacement is 15 meters, so you'd say delta x equals 15 meters. So go ahead, hit pause, try 2 through 7, and we'll come back. All right, we're back. Number 2 says a baseball is released and falls down a distance of 50 meters. And this is actually kind of interesting because you can actually get a couple different variables from this problem or from this statement here. A baseball is released means that its initial velocity, so initial velocity, remember, is VO. And since it's a baseball being released, we're going to assume it's going to fall down because gravity acts down. We could say VOY in this case would be equal to the number 0. So if they ever say in the problem a baseball is released, remember that means your initial velocity in the y direction is 0, and it falls down a distance of 50 meters. Well, in this case, the baseball is going down, so that means its change in position in the y direction, or its vertical displacement, delta y, is going to be 50 meters. And there's one little trick to this. Sorry, I'm not the best at writing this little tool here, but since it's going down, we'll say negative 50 meters. And then another thing you could actually add on here is you'd also have gravity is equal to negative 9.81 meters per second squared. Number 3, a soccer ball is kicked upward with an initial velocity of 20 meters per second. So initial velocity, as soon as you see that again, you're thinking VO. And then the word upward signifies the direction. So that means this is your initial velocity in the y direction. And then again, you also have gravity on this problem. The acceleration from gravity, or little g, is negative 9.81 meters per second squared. Oh, and I kind of gave away the next one. It says number 4, the acceleration due to gravity. They're basically telling you your acceleration in the y direction, which we usually just shorthand it and say they're giving you the value of gravity there. Number 5, a hockey puck is dropped. Hockey puck is dropped. Well, in all honesty, it's the same, very similar to number 2. So hockey puck is dropped means that your VOY is going to be 0. So since you're dropping something, you got VOY is equal to 0. And then you also know, in this case, you're assuming you're on Earth, your gravity, you have little g, the acceleration from gravity. Number 6, final vertical velocity is 2 meters per second. So final vertical velocity, so velocity, remember you're going to use v, and then vertical, you think, okay, well that's going to be v sub y. So in this case, final vertical velocity would just be vy equals 2 meters per second. And then last but not least, a plane flies a distance of 500 miles. And when we say something like this, we're going to assume that for the most part when planes fly, they're flying horizontally. So this would be the case where they're giving you delta x, or your horizontal displacement. If you put delta y there, that means you probably have a rocket ship, because that means that would be going up. All right, now we're all warmed up. So here's the deal. If you could grab a brand new blank page in your notebooks, we're going to put all of our motion equations in one spot. So someday if you take college physics, you can go back to this page of equations and be like, I remember I put these in one spot, one safe spot, where I just have them. I can use them in the future. But on the top left, if you could put general equations. So those are going to be the equations we've kind of used before. And then we're going to kind of convert those over to our projectile equations, or 2D motion equations. So take a moment, hit pause, copy this little chart down. All right, so thinking back, one of the first equations we used for kind of our general motion unit was delta x is equal to VO times t plus 1/2 at squared. And we use that for things like a train traveling for a certain amount of time, or a car accelerating for a certain amount of time, and you wanted to figure out how far it went. And then after we used that one side to side, we said, okay, let's convert that over to the vertical direction, which we just basically changed our x's to y, because things are going vertically now. And instead of just having VO, we had VOY, or voy, because it's your initial velocity in the y direction. Time is just time, because time is a scalar. It does not have a direction. And then what's kind of cool here is we said, okay, acceleration, maybe for a train or for a car, that's not what it's going to be when something's dropped. Whenever something's dropped, it's just acceleration equal to the acceleration from gravity, or little g, which is negative 9.81 meters per second squared. So we converted that equation to that one, and we said, okay, let's take this equation that we used in the x direction, and let's convert it over to the y direction. So we said v becomes vy over here, or your final velocity in the y direction. VO becomes VOY, and then again, wherever we saw the a, we just replaced it with the g, because things, when they fall, they gain speed due to the acceleration from gravity. And then we had this is called the time independent equation, because it's the kinematics equation with no time. And we said, okay, let's convert that one over as well. So we said our v's become vy's, vo becomes voi. And then instead of having delta x here, we had delta y. So things were falling. We want to figure out the vertical displacement. Well, what's kind of cool, now we're saying we're going to launch something through the air at an angle. And what we're going to do is we want to take our original kinematics equation and convert it over to something we can use for projectile traveling like through the air, right? So what we said is that when you throw something, gravity only acts in the y direction. So what's going to happen here is horizontally, objects don't have any acceleration. So a is equal to 0 in the x direction. And why that's nice is because that means that this whole term will go away. So our equation for the horizontal direction is just going to be delta x equals vox times time. And that would tell us how far horizontally it traveled, or its horizontal range. Now, if we take this equation right here and we say, let's try to come up with an equation for the x direction. Well, I'm going to put a little subscript x here and a subscript x here. But again, since acceleration is equal to 0, because things do not accelerate horizontally, like when you throw a baseball, if you throw it at 50 miles per hour, playing catch with somebody, they're going to catch it at 50 miles per hour if you were to throw it horizontally, pretty close, right? So that means this term goes away. And then our next equation says Vx equals Vox, which, think about what that is really saying for a second. And if you have to hit pause, you have to hit pause. But that means your final velocity in the x direction is equal to the initial velocity in the x direction, which means if your velocities are equal, initial and final, you're not accelerating. And then go ahead and try this one. How would we take this last equation and convert it over to a projectile motion equation in the x direction? And if you do that, you're going to get a repeat. You're going to get basically that Vx equals Vox again. So really, when you look at all these equations, really you only get two new equations, and they're right here. And the big note, you want to like put a triple star or quadruple star by this. The time that's in our y equations is the same time that's in our x. So time is the link between the vertical and horizontal directions. So if you ever feel like you're stuck and you're like, oh, I wish I had the time for this equation, there's a good chance you're going to have to kind of flip back and forth between being in the x direction or being in the y, and use time as the link. All right, so I just wanted to show a good example from AVHS soccer projectile in action. So basically, it's a good example of somebody putting a force onto an object, and that object is going to travel through the air here. So take a look. Game winner right there. Pretty cool. So if we back this up here, I think I should be able to do this. When that student first kicked the ball, notice it went up. So they kicked it kind of at a 45-degree angle. And if they kick it at a 45-degree angle, that means it's moving through the x and the y direction. So we'll watch it one more time, but notice the velocity of the ball changes vertically. Like it's slowing down as it gets to its apex, and then it starts to speed back up. But side to side, the ball actually doesn't really change speed that much. So what this really shows really well is that gravity only affects the ball vertically. It does not have any impact on its horizontal speed. So take again a look. You're looking is that it's going to change velocity up and down, but side to side it pretty much stays the same speed. So take one more look here. Pretty cool, pretty